Welcome to the virtual lecture on Chapter 2, The Chemical Basis of Life, Part 1. In this chapter, we're going to be covering general chemistry. And the reason we cover the basics of general chemistry, also known as inorganic chemistry, is because to truly understand the underlying mechanisms behind biological phenomena, like, for instance, metabolism, how we turn our genes into our physical traits, how we move. So anything relating to biology always goes back to chemistry, because living things are made of chemicals, molecules. Everything on the planet that is considered matter is made up of molecules. So we're headed to Chapter 3, where our focus is going to hone in on specific molecules that pertain to life and carry out the functions of life. And we call those biomolecules. So there are 4 classes of biomolecules: carbohydrates, lipids, nucleic acids, and proteins. But before we get into these larger, slightly more complex biomolecules, we have to have a basic understanding of all chemicals, all chemistry. Okay, so chemistry is at the foundation, really, of all biology. You can't escape it. So as I just said, everything in the universe that's not empty space is considered matter. And matter is made up of building blocks called atoms. And atoms are basically the building blocks of the universe. They're structures that can't be broken down by normal chemical reactions. So your entire body is made up of atoms. Okay? Not only that, all non-living things are made of atoms. So for instance, the air that you're breathing, the oxygen, CO2, the ground, the soil, water, these are all made of atoms. So a specific version of an atom is called an element. There are about 92 naturally occurring elements on planet Earth. We're not going to focus on most of those. We're only going to focus on the elements that pertain to life. So let's take a moment to look at how these elements are organized. So this is a periodic table. And we're going to primarily deal with elements in the upper right-hand corner. Elements like carbon, for instance, C, nitrogen, oxygen, chlorine, phosphorus. That's about it. Okay? Hydrogen. So we're going to ignore most of this table. Okay? We're just going to focus on the elements that are important to life. And I want you to realize that, first off, 60 to 70% of your body is water, because as we're going to learn, the solution in our blood and inside all of our cells are water-based solutions. Okay? So that's a molecule. Most of your body is water. But other than that, you're composed of those 4 classes that I was talking about: carbs, lipids, proteins, and nucleic acids. And those 4 classes of biological molecules are primarily made up of just 4 elements. And those 4 elements are oxygen, carbon, hydrogen, and nitrogen. So around 96% of your entire body is made up of just those 4 elements in various ratios. Now that's not all. You have many micronutrients, dissolved salts like ions like sodium and calcium and magnesium and iron, but you have those in trace amounts. So next we're going to take a closer look at a single atom. So a single atom has smaller parts to it, which we call subatomic particles. And an atom is composed of 3 different subatomic particles. The first 2, neutrons and protons, are at the core of the atom. And the neutrons and protons are together, and collectively they're referred to as the atomic nucleus. It's really heavy relative to the rest of the atom. And so neutrons, these are subatomic particles that have no electrical charge. They're neutral. Each proton has a single unit of positive charge, +1. And then surrounding the protons and the neutrons are the third type of subatomic particle, the electrons. So here we have that basic structure of an atom depicted. Here they chose a very simple element, helium. And you can see what I was talking about. So here's your atomic nucleus, that dense core in the center. So helium has 2 protons in pink, right? They have positive charge. 2 neutrons in brown, they're neutral. And then surrounded by the 2 electrons. So the electrons, which each carry a single unit of negative charge, they're attracted to the protons. So they're found circling or orbiting the atomic nucleus. And then there's a lot of empty space in between the electrons and the atomic nucleus. And I refer to this style of a diagram of an atom on the right as a cartoon diagram. So when you're doing the homework assignment for chapter 2 and it asks you to draw a cartoon diagram of a particular atom, you want it to look something like this, where you actually draw out all 3 types of subatomic particles. But moving forward, we're going to start to ignore the atomic nucleus and just draw it as a dot or a circle and just focus on the electrons. Next, I want you to realize that the periodic table provides all the information that you need to answer general chemistry related questions. And you will always be given a periodic table to use at your disposal. So you need to know how to access that information and interpret it, but it's all here laid out in this table. So we're going to look at various elements and we're going to explain the numbers that are provided here and talk about what they mean. And the first number that we're going to focus on is usually at the top of this little square. Okay, so here's carbon, C. And if you see just above the letter C for carbon, there's a number 6. Okay, so that's the number I'm talking about. That is referred to as the atomic number. Very important. Okay, so here's what I'm talking about. So here's carbon. This is our atomic number. Very important because it gives you a lot of information. It tells you 2 things about a carbon atom. The first is it tells you the number of protons that every carbon atom has. Okay, so that number is 6. So we can say carbon has 6 protons. Now, for a particular element, you can't change the number of protons. So what I'm saying is carbon always has 6 protons. Nitrogen always has 7. Oxygen always has 8. So if you change the number of protons, you change the identity of the element. So that really identifies which element you're talking about, the number of protons. But not only that, the atomic number also provides the number of electrons, unless otherwise stated. I say unless otherwise stated because as we're going to learn, elements can become electrically charged. They can actually lose or gain electrons. Okay? But assuming that hasn't taken place, we can assume that the atomic number is equal to both the number of protons and the number of electrons. So looking again here at our example of carbon, atomic number 6, we can say carbon has both 6 protons and 6 electrons. So let's pick one more example here. This element that we're going to pick is oxygen. The symbol for oxygen is just the letter O. And let's try to find the atomic number of oxygen, its number of protons, and its number of electrons. So the first thing we want to do is we want to go to the periodic table and look for oxygen. I'm already clicked on it. There's oxygen. And we can see that the atomic number at the top is number 8. So I'm going to use my notes just to write this out for you. So oxygen, okay, that's the chemical symbol, O. Atomic number 6. So what does that mean for us? That means that oxygen has 6 protons and 6 electrons. Okay, very basic, simple example. All right, moving forward to some of the other information provided by the periodic table. And the second number we're going to focus on is this number here found at the bottom. Now this is known as the relative atomic mass. It's basically the weight of that single element. Now in this class, I'm not going to focus on the relative atomic mass. I'm going to focus on a simpler term called the mass number. So instead of giving you a number that has a decimal like 12.01, you're always going to see a whole number. So for instance, for oxygen, I wouldn't put 15.999. I would write it as this. (16). And I just realized, little mistake, I was thinking of carbon when our example focused on oxygen. So you probably caught this, but the atomic number of oxygen is not 6. The atomic number of oxygen is 8. That changes things up a little bit. So let's fix that. Change that in your notes. Which would then mean that the number of protons for oxygen is 8. The number of electrons is also 8. Okay, but we're talking now about this bottom number, the mass number. And that mass number, which I will always provide as a whole number, is equal to the number of protons plus the number of neutrons. So here for oxygen, I'm telling you the mass number, the weight, is equal to 16. And I also said that number is equal to the number of protons plus the number of neutrons. So we already know the number of protons for oxygen, that is 8. So we can use this mass number to figure out the number of neutrons. So if we do 16 minus the known number of protons, that will give us the number of neutrons, which is 8. So I just did a simple little equation. I just did the mass number minus the number of protons, which is the atomic number, to help us find the number of neutrons. So then why in the periodic table is the number provided as a decimal? That is because there are different versions of each type of element existing in the universe. Some are more common than others, but for every element, there are slightly heavier versions of it that exist in trace amounts in the universe. So for instance, for carbon, the most common form of carbon is this. A carbon atom with 6 protons, 6 neutrons, and 6 electrons. 99% of all carbon on the planet is like that. But there are also more rare, heavier versions of carbon. For instance, carbon-13 and carbon-14. So these other, more rare, heavier versions of a particular atom are called isotopes. Okay, so these are the 3 common isotopes in this case for carbon. And isotopes differ from one another in their number of neutrons, and that is it. Now, they're all still carbon because they all have 6 protons, but you'll notice as you move from left to right, they get a little bit heavier because each isotope has 1 more neutron in the atomic nucleus. Okay, so the way I wrote this here on the left, this isotope of carbon, the most common, we can also write it like this. We can say carbon dash 12. So carbon dash the mass number. That's another way to state that. Okay, so we are ready to move forward and focus on the third and most important subatomic particle, and those are the electrons. And they are the most important because it is the electrons and the way that they are distributed around the atomic nucleus that determines how a particular element behaves chemically, and therefore what type of chemical bonds it likes to form. Does it like to form molecules, compounds, Does it form hydrogen bonds, covalent bonds, or ionic bonds? All this information relates to the electron distribution for that element. So as we said earlier, electrons have a single unit of negative charge and they orbit or circle around the atomic nucleus. And they don't just orbit around the atomic nucleus randomly. They follow discrete specific paths known as shells. So I want to take you through those shells. So the first and innermost shell is known as shell number 1. It's a little crooked. I'm going to redo that. Even worse. Let's make it bigger. There we go. Shell number 1. The second next outermost shell, shell number 2. And then moving outward, if you have electrons out this far, shell number 3. So I'm going to label those. We're primarily only going to talk about shells number 1 and 2. So this would be shell number 1, number 2, and number 3. And you can think of these shells as kind of like the tracks that surround, or the track that surrounds a football field. It's these lanes that electrons stay in as they circle and orbit around the atomic nucleus. And then here in the center, in purple, this is the atomic nucleus, which signifies the protons and neutrons. Next, these shells each hold a certain amount of electrons. So going back to this drawing, shell number 1 holds up to 2 electrons. And once it has 2 electrons, it's considered to be full. And if you need to add numbers 3, 4, 5, and so on, they would be added to the second shell. Shell number 2 holds 8 electrons, and so does shell number 3. Our next concept: how do we know where these electrons go on these shells? How do we properly fill our shells with electrons? Very important. And there's a process to it. So, to show you how this process works, it's easiest to start with an actual example. And that example that I'm going to use is oxygen. So I'm going to go back to this picture here, and I'm going to erase what we have here. Oops. I'm going to erase just the shells. Okay, so in our first example, we're talking about oxygen, and if you go to the periodic table, you will see that the atomic number for oxygen is 8. So again, that tells us that oxygen has 8 protons, and more importantly for us now, 8 electrons. So the question is, how do we draw out those 8 electrons? So let's start with shell number 1. So remember, shell number 1 holds a maximum of 2 electrons, but we need to get all the way to 8. So we're obviously going to fill shell number 1. Let me pick a different color for electrons. Let's go with blue. And I'll draw my electrons as little blue circles. So, electrons 1 and 2. Oops, gotta change my tool. Electrons 1 and 2 are located in the first shell. And there we go. It's full with a maximum of 2 electrons, but we have 6 more to go. So we need to draw a second shell. There we go. Now here's the trick. You don't just put these electrons in the second shell anywhere. There's a particular way you have to do it. And the way you do it is you treat this shell like it has four corners, kind of like a compass, like north, south, east, and west. And you place electrons at each of those four corners first, before you start to pair them together to get to a total of 8. So let me show you what I'm talking about. So we need to get to 8, we're at number 2. So here comes electron number 3. We're going to put it at one of the four corners. Here comes electron number 4. Now you're not going to put it anywhere, you need to put it at one of the 3 other corners. So there's fine. Also, on the left would have been fine. Doesn't really matter. Now we're ready for electron number 5, 6. And now that we have electrons at each of the four corners, we can begin to pair them. Now there's some information that I'm leaving out because this is not a chemistry course. Within each shell, there are like sub-lanes called orbitals. And electrons exist in these orbitals, oftentimes in pairs. Okay? So that's why I'm pairing these electrons. So where are we at? We're at 1, 2, 3, 4, 5, 6. We have 2 more to go. So now, for number 7, we will pair them. Now I picked the top, but I could have picked the bottom or any of those lone electrons. I'm just going to move in a clockwise manner for consistency. That's number 7. There's number 8. Now you can see this second shell is not quite full. It has 6 electrons located in it. Remember, the second shell holds a maximum of 8. Now this is really important. The reason that atoms come together and join together to form molecules held together by bonds is because atoms want full shells. They want their shells full of electrons. So whatever the outermost shell of that element is, in this case for oxygen, it's the second shell. Oxygen really wants 8 electrons in that shell. It's not happy with 6. It wants 2 more. So let me show you what I'm talking about. Let's change the color here. It has 2 empty spots. It could put 1 more right there at that X and 1 more right there. So it really wants to fill those 2 X's with electrons. You might wonder, why? Who cares? I'm not really sure why. Has to do, it's kind of a fundamental principle of the universe, is that atoms are more energetically stable when they have full outermost shells. So all atoms are looking to have that stable state. And we have different names for that state of having a full outer shell. So first I want to define a new term. And that term is valence. Specifically, valence shell. And the definition of that term, it is the outermost shell of an atom. So expanding on what I just said earlier, we can say that every element or atom is striving to have a full valence shell, a full outermost shell. And another term for that, a full valence shell, another term is an octet, which means it's full, it has 8 electrons, it's happy. Okay? So that explains pretty much all of chemistry and all of biochemistry. Elements are looking to fill their valence shells. And they do so in different ways. Sometimes they share electrons with nearby atoms. to help each other both achieve octets, full shells. Sometimes one atom really wants an electron, so it rips away and steals one from another atom or two. Okay, so there's different ways to go about it, but all atoms are looking for that state, that happy state of an octet. All right, so since this is so important, let's do one more example. Let's pick a different element. That element will be carbon. And I'm not going to do so, but the first thing you want to do is jump over to the periodic table to find out some information about carbon, but I will provide it for you. Carbon, atomic number 6, which means that it has 6 protons and 6 electrons. So same thing, let's properly draw out these 6 electrons. First things first, shell number 1. And remember, shell number 1 holds 2 electrons. So there's number 1, there's number 2. Done, but we have 4 more to go. So we're going to draw our second shell. And remember, the key is to place electrons at each of the 4 corners before beginning to pair them. So here comes electron number 3, 4, 5, and 6. And I picked this example of carbon because carbon is the most important element for life. It is the backbone of all biological molecules, your carbs, your fats, your proteins, and your nucleic acids. And the reason for that is it's because of carbon's unique electron distribution in its second shell. So if you look here, carbon by itself, not very happy. It's pretty far away from an octet, right? It wants 8 electrons in that second shell. It's only half full. It only has 4. It wants an electron here, 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 and here. So it needs to do some work to achieve that state of an octet. And as we're going to learn here moving forward, it's so important to draw your electrons out like this, in this specific way, because it tells you the number of chemical bonds that that atom forms in nature. So these X's are really important because that tells us the number of bonds that that element will form. So for instance, carbon forms 4 chemical bonds. If you go back to the drawing we had previous with oxygen, it needed 2 more electrons, so it had 2 X's. Therefore, oxygen forms 2 chemical bonds. So it's really important information. And another term here, since carbon needs to form 4 bonds, that's the maximum number, okay? So it has something called tetravalence. It has the potential to form the maximum number of chemical bonds. And that's why it's the backbone. If you're building a bigger molecule, your molecule can branch out in 4 different directions. You can build bonds in 4 different ways. Okay? Towards you, away from you, up, down. So carbon is the cornerstone of all biology. So here we see what I was just talking about. The number of electrons in the valence shell determines the number of chemical bonds that atom tends to form in nature. Now, another thing that the periodic table does is that it organizes your elements by electron distribution. As you move from left to right, top to bottom. So as you move from here to 2, to 3, to 4, to 5, each time you move one element, you're putting one more electron into the shell. So here's carbon, which we just drew. Nitrogen, which has one more electron, looks like that. Oxygen, like that, until you get to neon, where it has an octet and it's full. And that brings up a point here. The reason why you've probably never heard of neon in your body or argon or any of these elements here on the far right, that's because they don't form chemical bonds. They are already happy. They already have octets. So they don't participate in chemical reactions. They don't make up your body, you know? So we largely ignore these elements in biology. These are the noble gases. They're noble because they're happy by themselves. They already have octets. All right, so we're moving forward to chemical bonds. And we said that every atom forms one or more chemical bonds to achieve an octet, a full valence shell. Now, there are two general ways that an atom can attain an octet. The first is it can share electrons with another atom. And if two atoms that are in close proximity to one another share electrons, we call that a covalent bond. So think of covalent as being synonymous with sharing. Then we'll talk about another type of chemical bond where one atom actually steals an electron from another atom. So one's going to lose an electron, one's going to gain an electron. So there's a transfer. That's called an ionic bond. And we want to define and distinguish between two different terms here, and those terms are molecules and compounds. So first, let me state their definitions. A molecule is composed of two or more atoms held together specifically by covalent bonds. And those atoms are always existing in a fixed ratio. So for instance, water is H2O. There's always 2 hydrogen atoms for every 1 oxygen atom. A compound is 2 or more different atoms held together by chemical bonds, which can be either covalent or ionic, but still the atoms are in a fixed ratio. Now, kind of tricky definition, so it's easiest to explain by giving you actual examples of molecules and compounds. So let's start with molecules. Remember, these are specifically held together by atoms that are sharing electrons. So I'll start simple. One that you're currently breathing in. Let's go with oxygen gas. It's 2 oxygen atoms forming bonds together. That's a molecule. It's 2 or more atoms forming a covalent bond in a fixed ratio. Another example. Water. That fits our definition. two or more atoms in a fixed ratio held together by covalent bonds. I'll give you one more or two more. The list is endless here. Carbon dioxide, CO2. Let's do a bigger one, glucose. A type of sugar, C6H12O6. These are all molecules. Give you one more, hydrogen gas. Now remember, a compound's a little bit different. It's specifically two or more, keyword different, atoms held together in a fixed ratio. So there are two molecules on our list here that are not compounds. Okay, and that's oxygen gas and hydrogen gas, the first two. They're not compounds because it's not two or more different atoms. But the others fit both definitions. So for instance, water, you can say it's a molecule and it's also a compound. Either term works. So is CO2. It's two or more different atoms held together in a fixed ratio by covalent bonds. So is glucose. Now you're probably wondering, how does he expect me to know that water or CO2 are held together by covalent bonds? How does one recognize that? And you're not expected to know that. You would always be given that information. But anyways, those are the three compounds that are also molecules. But remember, I also said compounds include atoms held together by ionic bonds. So those, as we're going to learn, are salts. So that includes things like table salt, sodium chloride. Just going to give you three examples of salts. Okay, so those are also compounds. They are not molecules, those last three, because they're not held together by covalent bonds. As we're going to learn, salts are held together by ionic bonds. So not super important, but I oftentimes use the word molecule unless I'm talking about a salt, because I can't be wrong, okay? Because it fits both. But that's the specific definitions to it. Now the first type of chemical bond we're going to talk about here in chapter 2 are covalent bonds. And as we said earlier, these are bonds that involve two or more atoms sharing electrons to help each other achieve octets. So the key word in this definition is sharing. Now remember, the big four elements in biology are carbon, hydrogen, oxygen, and nitrogen. Now those four elements, as they relate to biology, always form covalent bonds. And you can always figure out the number of covalent bonds that each of these four elements will form by looking at the number of unpaired electrons in each of their valence shells. So for instance, we looked at carbon, right? We saw carbon had 4 X's, right? 4 unpaired electrons. So we said, hey, carbon forms, or is looking to form, 4 covalent bonds. That same rule of thought applies to all 4 of these elements. A few things about covalent bonds in general. They are the bonds of life. These are really strong bonds. You can't break them unless you have extreme heat or an enzyme. Okay? So they're so strong they don't dissolve in water, which is a nice thing because your body is, almost 70% water, and you don't want your carbohydrates and all your molecules just falling apart in water. You want them to be held together. Okay, so the strongest type of bond we're going to talk about by far Okay, so they don't dissolve, they don't break apart in water. And as we move forward, we're going to see that there are two different types of covalent bonds, known as polar covalent bonds, and the second is known as nonpolar covalent bonds. And here we're going to talk about one of the two types, and the first type we're going to talk about are polar covalent bonds. So the reason that there are two different types of covalent bonds is because two atoms participating in a covalent bond do not always share their valence electrons equally. There are some cases where one of the atoms in the bond has a higher affinity for electrons, meaning it likes electrons a lot more than the other atom. So it's kind of like there's a tug of war. You know, they're trying to share this pair of electrons. They both want it, but sometimes one of the atoms is stronger than the other. So it pulls those electrons closer to it. So that is the type of bond we're talking about here, where one atom is stronger than the other, has a stronger pull or affinity for electrons. So polar covalent bonds involve a pair of electrons that are not shared equally. And the technical term for the atom that likes electrons more than the other, we say that the atom that likes electrons more is more electronegative, which just means it really likes electrons. So you might be wondering, well, why do some elements like electrons more than others? Well, the answer has a lot more chemistry to it, but in a simple sense, if you look up at the top right-hand corner of the periodic table, where you have elements like oxygen, nitrogen, fluorine, chlorine, pretty much those elements are the most electronegative. They have a really strong pull for electrons. And the way to remember that is that they are very close to octets. Like for instance, fluorine has 7 electrons in its valence shell. It just needs one more to get that octet. So it really, really wants just one more. Same with chlorine, it has 7 in its outermost shell. It really wants one more. Oxygen only needs 2 more, so it just really wants to fill those 2 spots. So they'll do anything they can to get those electrons. For us in this class, all you need to know is that oxygen is the most biologically relevant electronegative element. Okay? So whenever you see oxygen, O, right, in this class, think it really, really likes electrons. That'll explain so much in these first few chapters. So, when oxygen is sharing a pair of electrons with another element, another atom, oxygen, in a sense, is going to hog those electrons because it's stronger. And because of that, those shared electrons are going to spend more time near the oxygen atom. You only need to know one example of a polar covalent bond in this class. That's it. And the one example is when you have a bond between an oxygen atom and a hydrogen atom. So when they share a pair of electrons, it's always a polar covalent bond. And those electrons, which I'll draw right now as two little dots, are going to spend more time near oxygen. Okay, so that's very important to know that. And remember, electrons are subatomic particles that have negative electrical charge. So if you have 2 electrons spending more time near the oxygen atom, right, they're circling around, that's going to make the oxygen atom more negatively charged. And conversely, since the electrons are going to be spending less time near hydrogen, it's going to make that hydrogen area more positively electrically charged. Probably wondering, what is that weird symbol that you're writing before positive or negative? It just means in biology, partial. So partially negatively charged on the left, partially positive on the right. And that is where the name comes from. Polar covalent. It's like a North Pole and a South Pole, okay? There's a negative pole and a positive pole. Okay, there's differences in charge because of this unequal sharing of the pair of electrons. Now, there are various ways that biologists and chemists draw out covalent bonds. I'm going to teach you 2 different ways. The way that we're headed towards is this 3rd row here, where we denote a single covalent bond as just a solid line. But to understand that, we have to move backwards a bit. Okay, so we're going to show, it's kind of harder to draw, there's more to it, but it will help these drawings make sense. So we're going to start by drawing molecules out using something called an electron distribution diagram. Then we'll show how that represents these down here, the structural formulas. So we're going to start with the more tedious way, the electron distribution diagrams. And in this class, you are only responsible for knowing how to draw one molecule. And that one molecule is water. Okay, so we're going to use water here as an example for drawing molecules and as an example for illustrating covalent bonds. Specifically in this case, polar covalent bonds. So water, if you didn't already know, has the molecular formula H2O, 2 hydrogen atoms for every 1 oxygen. So let's draw it out. And I'm going to take you through 2 examples. I'm going to pick 2 molecules. One is going to be really simple. Hydrogen gas, H2. It's 2 hydrogen atoms. Then we'll jump to water. So let's do that. We'll start with the bottom example. And remember, we're going to draw out something called the electron distribution diagram first. Now, I don't have it set up for hydrogen gas, so let me just draw that in. So purple is going to represent, let's see. Purple is going to represent the atomic nucleus. Try to keep this the same color here. That's fine. So my first example, just trying to start simple here, is not water, but just this molecule right here, H2. 2 hydrogen atoms. Now hydrogen's a very simple element. It's atomic number 1. So if you go to the periodic table, you'd see that. So what does that tell us? Hydrogen has 1 proton, but also 1 electron. So that means we're only going to deal with shell number 1. Like I just said, it only has 1 electron. So we're going to put it right there. Now ask yourself, what does this single hydrogen atom really want? The answer should be, it really wants a full outermost shell. Now, the outermost shell of hydrogen is just the first shell, so it doesn't need to get to 8. It only needs to get to 2 to have a full valence shell. So remember, we like to put an X showing what that atom wants, right? The number of unpaired electrons. So hydrogen wants one more. Let's see. Can I copy and paste this? Give me one moment. Oh, I figured it out. Thought I did. That will save me from drawing the same thing twice. So we're trying to understand here, why does this molecule exist? Why do 2 hydrogen atoms like to come together to help each other out, to share, to achieve octets? And as we draw 2 hydrogen atoms adjacent to one another, it becomes clear. If they get close enough, they can be so close that their electrons orbit near both atoms, right? And they can actually use a different color. What color can I use? Let's pick green. They can actually share. I'm gonna put a circle around it. They can share those 2 valence electrons. So for this hydrogen atom on the right, it's happy. It sees that it has 2. Same for the one on the left. It's close enough to the other atom that it has 2 electrons in close proximity to the nucleus. So this is the simplest example of a molecule held together by covalent bonds. Now, the simpler way to write this would be this. Just focus on the covalent bonds. Now in this case, there's only one bond, so we write it as a solid line. So this on the left, the electron distribution diagram, is equivalent to the structural formula, which I have on the right. So this is the electron distribution diagram. This is the structural formula. And one more thing, this solid line denotes your 2 electrons. Okay, so it represents the 2 shared electrons. That's what the solid line means. All right, so that was my first example. Let's do the same thing, but with water. So luckily for water up here, I'm already set. Remember, water, H2O. So first, it has 1 oxygen atom, and if you remember, oxygen is atomic number 8, which means that it has 8 protons and 8 electrons. So the first thing we're going to do is distribute those electrons for oxygen. So we have 1, 2, 3, 4, 5, 6, 7, 8. And we'll put an X next to the unpaired electrons, right? Signifying that they want 2 more. So that's oxygen, so I'll put in parentheses the letter O for oxygen to show you that that represents oxygen. And well, oxygen likes to be involved with two hydrogen atoms. And if you draw the two hydrogen atoms next to the oxygen, it will make sense why that is. So hydrogen, again, pretty simple. Atomic number 1, it has 1 electron in its first shell. Each one wants 1 more. Now, you can see why oxygen and the two hydrogens can make each other happy. I pick the color green again. They can share valence electrons. That's one pair that they can share. It's not going to be perfectly uniform. That's the second pair. Okay. Now I could turn this so it's a nice triangle shape, but I'm just going to keep it how it is. That's water. And you can see every atom here has an octet. The two hydrogens are happy. So this hydrogen here, it has 2. It's close enough to the oxygen so that it sees that it has 2 electrons. It's full. Same with the hydrogen here on the right. It's got an octet, it has 2. And then finally, oxygen at the top is happy. It filled those 2 vacancies, and now it has 8. So everyone's happy, everyone has an octet. That's it. So that's the tedious electron distribution diagram. Let's convert that into the structural formula. So remember, for the structural formula, we just put the symbol of the element. So instead of this whole mess at the top for oxygen, we're just going to write the letter O. And instead of these circles here on the left and the right for hydrogen, we're just going to write the letters H for each hydrogen atom. And remember, with the structural formula, the only thing we want to focus on is covalent bonds. So how many covalent bonds do we have? We have 2, 1 here, 2 here. So again, those green ovals represent the covalent bonds, the shared pairs of electrons. There are 2 of them. And what's our shorthand way of denoting these covalent bonds? The answer is a solid line. So here's one pair. Here's another. That's a little crooked. I want to redraw that, but you get the point. Let's see. There we go. That's the most common way to illustrate water. And again, what do these solid lines represent? They really represent the 2 shared pairs of electrons. But remember, everything that we're talking about here in this first part is dealing with polar covalent bonds. So remember, oxygen loves electrons. So those electrons aren't going to be perfectly shared down the middle. Okay? Oxygen is going to win these 2 tug-of-war battles with the hydrogen atoms because oxygen is really strong, really loves its electrons. So let's better illustrate that. Oops. So in reality, those electrons are going to be more over here, closer to oxygen. And very importantly, that creates electrical poles, or a discrepancy in electrical charge across the entire molecule, meaning that since the electrons are spending more time near oxygen, Oxygen is more negatively charged. So there's a region of partial negative charge there. And again, since the hydrogens are seeing less of those negatively charged electrons, it's relatively positive down there near the hydrogens. And it's this simple illustration that explains why life is dependent on water. So all of the life-supporting unique properties of water emerge from the fact that water is a slightly electrically charged it's a slightly electrically charged molecule. Okay, it has the tendency and the capability to stick to other things that are of opposite charge. So the oxygen, which is negative, can stick to something that's positive. And vice versa, the hydrogen, which is positive, can stick to something that's negative. So keep that in mind. That's a very unique property of a water molecule, to have charge. So this summarizes here everything we've just covered. We've completed all of this. This is just another way to depict a water molecule. It's called the space-filling model. And at this point, we've covered one of three types of chemical bonds. We've covered this one here in the center. And this is showing how the electrons are shared. So it's showing this would represent, for instance, oxygen. This would represent hydrogen. Okay, so oxygen's winning that tug of war. The electrons are going to spend more time near oxygen. An unequal sharing of electrons. Thank you for listening, and make sure to tune in to part 2.